started. So today we will have motion planning lecture number 10, and our topic will be optimization-based motion planning. Before we start, just a reminder, there's a course evaluation on the ISIS platform, so it would be good if you can just fill it out. Yeah, it's the third time that we give this lecture, and every time we get feedback, we can improve upon it, and so we can make it better for the next class. Okay, so last week Wolfgang talked a little bit about completeness and convergence of RT, also about asymptotic optimality and how you can prove it, and also a little bit about more advanced sampling-based planners, for example, lazy PRM, FMT star, and I think also SST star. And yeah, if we look at the whole lecture again, we had three big topics of how we can actually solve motion planning problems. So in the beginning, we talked a little bit about search-based planning, where you had kind of a grid or a graph on your configuration space, and you use planners like A star. Then we shifted a little bit to the second big topic of sampling-based motion planners, where you sample the configuration space to find paths. And now we come actually to the third bigger topic of this class, which is optimization-based planning. And for today, we will have basically three big topics. One is that I will give you a little bit of an introduction to convex optimization, because it's super important in a lot of different optimization-based planners. Then a small introduction to this general topic of optimization-based planning, and then we will go a little bit into details of splines, of gradients, also on motion paths, and also we will talk a little bit about signed distance fields, because they are also super important to compute costs on paths. Okay, and so first topic for today will be convex optimization. So with convex optimization, let me first start with general optimization. So if you want to optimize, for example, a function f, which goes from Rn to R, this could be something like a cost function. Usually we write this here as finding x such that you minimize this expression here, so that you find the argmin of f of x. So this basically means you have a function here on your Euclidean configuration space, for example, and this could be a cost, and you want to find out which configuration here actually minimizes this expression. So usually this is not super useful, because often you have a lot of different constraints on your configuration space, and so something which we actually are interested in is constraint optimization. This is basically the same as unconstrained optimization, but we have two additional functions. One is g and one is h, and g encapsulates all inequality constraints, and h encapsulates all equality constraints. So for example, if you're in a 3D space, you could think about g as something where you constrain something to like a half space or a region of the configuration space, and h could be something where you constrain to a plane or a line segment. So this is basically the general structure of optimization problems. And usually we also make a distinction between optimization problems depending on the nature of f. So if f can be evaluated, then we call this a black box optimization. And if there are no derivatives which we can compute of f, then this is black box. If we can actually compute the first derivative, then we call this a gradient, and we can also have problems which are second order, where we can actually evaluate also the second order derivative of f. So, and of course, the more derivatives you can compute, the more additional information you have, and in general, it's a bit easier to solve the more information you have, of course. So, I would say almost everything can be casted as an optimization problem, and in the end, it's also super important to figure out if something is, has derivatives to make it faster. Okay, and in terms of solving optimization problems, we usually employ like two big ones. One is gradient descent, especially for the unconstrained case, and the second one is augmented Lagrangian. This is basically where we convert constraints from our constrained problem to an unconstrained problem. And in general, if you do optimization with this formulation here, this is basically a local approach, which means that most algorithms are local and only provide you a local solution or a refined solution around an initial guess. And something which is very, very important for optimization is this concept of convex optimization, because if you actually can cast your optimization problem as a convex optimization problem, then everything gets a lot easier. And so let me give you just a small introduction here to convex optimization. So the first thing which is important for convex optimization is this concept of a convex set. So the idea is basically that a convex set is something where whenever you have 2 points in your set, and you draw a line between them, a straight line, then this line has to be strictly inside of the set. So for example, this set here is convex because whenever you choose 2 points, x and y, and you draw a line between them, then the line will also be inside of the set. And so mathematically, this is just formulated as a linear interpolation between those 2 points, and we have to make sure that for every 2 points in our set, we basically have to ensure that the linear interpolation here is also inside of the set. So this is the idea of a convex set. Another concept which is important is the one of a convex function. So we go back to this function f, which goes from Rn to R, and this function is defined to be convex if whenever you choose 2 points on this function and you draw a straight line, then everything of the function between those 2 points here are lying below the straight line here. So for example, you pick 2 points here, x1 and x2. You evaluate the function here at f of x1 and f of x2. You draw a line here, and then every function value between them in this range here between x1 and x2 has to be actually below the line. And if this is true for every x and y, or x1 and x2, then this function is actually called convex. And so mathematically, this is basically described as this function here, where you have on the left side the evaluation of f on all the points here between x and y, and on the right side you have the straight line between f of x and f of y. And you have this linear inequality, which states that everything on the line here is larger or equal to every element on f. So this is the concept of convex function. And so just to recap this, convex set, convex function, and now we want to actually put them together. And we can actually use it to define when an optimization problem is convex. And so we say the constraint optimization problem is convex if and only if f and g are convex and h is linear. So I'm sorry that you can't see this. I just move this away. Okay, let's get back to convex optimization. So the reason why we're actually interested in convex optimization is because this is global, it means that every local minimum in your optimization problem is actually a global minimum. So there's basically just one point which is it's a global minimal solution, and it is usually pretty good to have this guarantee. In practice, it's sometimes a bit difficult to find the minima in a predictable time, but usually if you can actually cast the problem as a convex optimization problem, then this is often, it's a big difference between having something which you can efficiently solve and having something which is not really efficiently solvable. And convex optimization problems can also be further refined into different optimization problems. So this is something which you can see here on the right. So CP stands for convex program or convex optimization problem. And you can see here that there are several problems which are subsets of convex programs. One is, for example, a linear program or linear optimization problem where everything is linear in terms of x. So f of x is basically a linear function of x, and the same here for g and h. And another big convex optimization problem which we're interested in is a quadratic program. This is basically something where g and h are again linear, but f is actually quadratic in terms of x. And so this is actually interesting because a linear program can be solved in polynomial time. So this is something which you can solve super efficiently. And a quadratic program is also interesting because if Q, this matrix here, is positive definite, and I think it's also when it's positive semi-definite, then it can also be solved in polynomial time. So whenever you can actually find a convex problem, that is pretty good, but if you can even find a linear program or quadratic program, then this is much better because now you are actually sure that you can solve it in polynomial time. Okay, so this was just a small introduction to convex optimization, and we will see later on how this can actually be used for optimization-based motion planning. Any questions for this introduction? Okay. So, now that we covered convex optimization, let's go straight into optimization-based motion planning. So first of all, what is optimization-based motion planning and how does it differ from, for example, search-based or sampling-based planning? The idea behind optimization-based motion planning is basically that you get some kind of input, path or motion, and you apply some optimization functions, and this gives you a much better, more optimized motion at the end. So for example, here on the left, you might have here a motion which might come out of a sampling-based planner. This has this zigzag motion here because we have made basically a random walk in space. And most of optimization-based planners can actually take a path like that and they can optimize it to get like something which is very smooth and optimal with respect to some cost function which you defined. And something which is also interesting is that there are a lot of optimization-based planners which can also take as input an infeasible path. So for example, if you have just here a straight line, this green path here, they can also take this as input and generate, for example, an output which is close to optimal and also feasible. And so this is basically the whole idea, that you get as input some kind of path which might be feasible, might not be feasible, and you optimize it so that you get an optimal solution. And so we will look mostly at some 2D problems. And again, the idea is basically you get some zigzag path as input and you want to produce something which is optimal with respect to some kind of cost function. Okay, and in terms of categorization of how we will look at optimization-based motion planning, we will make this distinction between two different types. One is gradient-free and one is gradient-based motion planning. So gradient-free means basically that you don't have to evaluate derivatives of your cost function. One method which we already saw and which we will also discuss a little bit is shortcutting, where you just improve your path locally by shortcutting segments. And then gradient-based is basically something where you have a cost function which you can also derive. You can take the first or second derivative and you use that as information to locally improve your path, and we will also look at different methods, especially splines and also jump. I also wanted to mention here COMO. This is a framework which Marc Toussaint has actually developed, which is also a super powerful framework for optimization. But today we will only look here at those three functions: shortcutting, splines, and jump. Let me just start with shortcutting. I think we already discussed that when we talked about PRM and RT, because it's basically that you always get back a very zigzag path, and of course this is not near optimal, and this is something very cheap which you can do is shortcutting. And so the idea in, I would say, the vanilla version is basically that you take that you sample two waypoints on your path and you try to connect them and update the path, and you repeat this just until timeout or convergence. So it's a very simple algorithm, works quite well in practice, and it's very easy to implement, and does unfortunately not take any complex cost functions into account. So I think last time we already talked about that this actually only takes cost functions into account which have a certain structure. And also, if your path is, for example, has too few waypoints, then very often it's very difficult to connect them. And if you have too many waypoints, then it can also happen that you have a very long computational time. So this is basically just a small reminder about shortcutting. Here again, some visualization. So just to show you again how this works, basically you have your path here, you take 2 points, you try to connect them, and if it's possible, you update your path, and you continue this, you take 2 new points, you try to connect them, you see this is infeasible because there's an obstacle here, and you continue this until your path gets smoother and smoother over time. So this is basically the whole idea. And now I have some questions for you. First question is, I already said that it's a bit difficult to take complex cost functions into account, but do you think actually that it's possible to do shortcutting with an arbitrary cost function? That's absolutely right. And so of course, if you only add an edge and you check if this shortcut is better, then this might be a problem for some cost function, because some cost function only operate on the whole path and they are, for example, not additive. And so you already said this correctly, that if you actually take the whole path cost into account, then this is actually possible. Yeah, very good. Second question, can you also do shortcutting on some weirder spaces, for example, a sphere, something which is non-Euclidean? Or is there something special you have to keep in mind?
On a sphere, the shorter path might be not, like if we plan a path around the circle, might be shorter to go the other way. So that
how would you do that?
I don't know how to do it on sphere geometry, but on a circle you could just check both ways. On a sphere, I think it's called weight circle distance or something.
Yeah, that's correct. But so for motion planning, how you would integrate it is basically just as a metric, and then you would just forget about the underlying structure. And the metric would basically just give you the shortest path, hopefully. Yeah, correct. And one last question about shortcutting. Can you also do shortcutting with a kinodynamic system? Yes.
I mean, I think we discussed it in the exercise already that you could potentially just like take a subtree and then rebuild that subtree and then use it as a shortcut, but you can't do direct shortcutting because you need to take the dynamic constraints into account.
Mm-hmm.
I mean, I think you can do shortcutting if you then check if the kinodynamic constraints are met. So, like if we have just like in the programming example we have currently, we can instantly change our direction in a given angle range, and we can also instantly change our velocity. And I mean, there are definitely feasible shortcuts that would be able within those kind of dynamic constraints. So I think it should be possible depending on the kinodynamics.
Mm-hmm. Okay, so you said it's not possible, you said it's possible. Who's right? Actually, you're both right, so it really depends. And it depends on the steering function. So if you can actually steer from one point to another point exactly, then this is basically the same as you would interpolate on a geometrical system. However, it's usually very difficult to compute steering functions, and so if you have a kinodynamic system which doesn't have a steering function where you can only forward propagate, then I'm actually not aware of any way of how you can shortcut this. So there might be something, but yeah, it's definitely harder, and you can't also go to a goal, for example, exactly. So you would at least need, for example, a bigger goal region and then forward propagate and try to end up there. Okay, cool. Yes?
But if you like do this planning for subsets of the existing tree,
Mm-hmm.
would that still be shortcutting?
What do you mean? So you want to do exact kinodynamic planning for a subregion?
Yeah, exactly.
Mhm.
Take like same as shortcutting, but basically use it as starting goal for new planning.
Yeah. So if you have a steering function, then this would definitely be possible, but if you can only forward propagate, you might never actually end up at the goal node. Yeah. Of course, if you don't care so much about exactness there, then it might be an option. But in general, that's not possible. Okay, any other question? Cool. Okay, then we will look at a second topic, optimization using splines. And before we go in there, just a small reminder of what splines are. So spline, actually the word comes from shipbuilding, where people used like planks to actually get the shape of a ship, and this was called a spline, and from this actually developed the mathematical definition, which is basically a piecewise polynomial function. And one question is, of course, why do we actually want a piecewise polynomial function interpolated between points? Anyone an idea of why we would be interested in that? Yes.
I think you want constant acceleration so that your river current doesn't exceed any limit.
Mm-hmm. So you want to basically have something more optimal compared to your original path. Yeah, that's definitely correct. Yeah, so first of all, of course, smoothness, differentiability also, and something which I also wrote here is comfort. So for example, if you're in a car and you have like a very zigzag path, then of course this would not be very comfortable. And so splines are actually pretty powerful to give you differentiability. And so if you, for example, can derive velocity and acceleration and maybe even the jerks, then usually motions are much smoother, and this would, for example, in the car give you much more comfort. Yeah, so definitely we want that because we are interested in more smoother paths, maybe also paths which minimize, for example, the energy spent along the path. Okay, and one of the bigger concepts for splines and also for smoothness is, of course, this concept of smoothness, which I just want to talk a little bit about. So smoothness is basically something which we define as that the path is at least n times differentiable. So we basically have for smoothness different differentiability classes, which we call C0, C1, all the way up to C infinity. And the higher a motion is in one of those classes, the smoother it is. So for example, if you have a discontinuous function, then of course this is not continuous and also not differentiable. And in this case, it would not be in one of those classes. Then a path which has like those corners, this path would not be differentiable at those corner points here. And so in that case, we would call that a C0 function because this would be continuous but not differentiable. And then, of course, if you have something which is differentiable everywhere, then you have a C1 function. And you can also do that for higher order functions. And something which is pretty important. So if you, for example, want to find out in which class your function is actually in, a usual trick which you can do is that you plot all the derivatives of a function. So for example, here, this could be the position of, for example, a motor joint on your robot. And here we have the velocity of the motor joint, and here we have the acceleration. And what you can see here is that the position is linearly increasing. The velocity, when you derive this here, you get this velocity profile here. And if you derive this velocity profile, you get this acceleration profile where we have in the beginning a small increase linearly, and in the end also a small decrease to bring down the velocity. And so if you look at all those three functions here, what do you think, what kind of differentiability class this function will be in? Yes?
From top to bottom, like C2, C1, and C0, because like the lower one is only continuable, but
Oh yeah, so it's the same function. So this is
yeah.
the function, and those are just the different
Okay, so
derivatives.
the function, the overall function would be C2.
Yeah, exactly. Yeah, and you can basically see this here in the third row that there are some points here which are not differentiable, and so we basically have to stop at this point here. And then of course if you want to have higher order functions, you need to also make the acceleration differentiable, and often it also makes sense to go to the next level, which is the jerk, and to also make this differentiable. Okay, and in terms of splines, we will look today a little bit at basis splines or B-splines. We will also look at polynomial splines, and then we will do a little bit of geometric planning with polynomial splines. And finally, we will look at Bezier curves, and we will look at a very interesting topic where we do safe planning with Bezier curves, where we look at regions in configuration space which are free and where we can actually plan inside of. Okay, so let me first start with B-splines, just a quick introduction here. so basis spline or B-spline is basically a polynomial function where you sum up different control points times a basis function. So usually what we do is that we take a path and we represent it by m control points, which we call Pm. And for each control point we have also a basis function. And the rules here are that the basis functions for each t along the path have to actually sum up to 1. And so for each point here on the path, you actually sum up the influence of each basis function times the control point. And so this interpretation of a basis function is basically that it gives you the influence of a control point, Pm, at a certain point t. So this is the idea. And so, yeah, graphically you can see this here. So for example, if you have 3 points here, P1, P2, P3, those are control points. Each of those points here has at time t a certain contribution, which is defined by their basis function. And so for example, the point P of t might be something here in the middle, depending on what is actually the influence of P1, P2, P3. And yeah, one of the more important concepts here is the one of a knot vector. So basically what you do to construct a basis spline is that you take as input a path on your configuration space and you cover it with m subintervals. Each subinterval goes from ti to ti plus 1. And for each of those ti, you actually define a basis function which is centered at ti. And yeah, ti we call the knot, and all the t's together is our knot vector. So you will see that in a second how this actually relates here to the basis functions. And now we can also define basis functions. So for example here we have on the right here ti. This is one of our points here from our interval, from our knot vector. And we can have, for example, a linear B-spline where we just have this linear profile here. And this is basically something where we define how actually the control points influence our path. And so if we actually visualize this for this example here with 3 linear splines, where each time here we compute the influence of green is basically the influence of the first point, blue is of the second, and red of the third. Can anyone tell me how the resulting path might look like on a linear B-spline? Yes. Yeah, maybe I should have actually showed you this example first. Yeah, yet.
I think really just lines connecting points, right?
Yeah. Yeah, exactly. So basically the idea is that you go along here, those 2 intervals, and at each point here you compute basis function times control point, and this gives you this linear interpolation here. And I also drew here the gradient of each of the colors, and this shows you what is actually the influence of the basis function at each point. So for example, if you're in the middle here, then both green and blue have the same influence, and this is basically the point here way in the middle, and then on the right here in the middle you have influence of red and blue, but nothing here from green. Okay, yeah, so this is basically super easy interpolation with linear B-splines, where you get just this linear interpolated path. Something which is a bit more interesting are, for example, quadratic or cubic basis functions. For example, here we have something which is called a Hermite B-spline, which is a cubic function in X, and this gives you this small, almost Gaussian-looking basis function, which actually gives you a more smoother influence of the of the control points. And if we also do the same here, where we have basis functions for each of the times, which are the influences of the control points, there is of course the question, how would this now look? Would that still be a linear interpolation? Or would the resulting path look different? Anyone an idea? Yes.
I think it would look different because previously the like influence radius of a point T1 was only until point 2. Now we've got influence until like the time step T3.
Mm-hmm.
So while we go from point 2 to 3, the point 1 will still have an influence. So it might look a bit more smooth out.
Yeah, that's correct. And will we actually hit one of the control points?
Well, yeah, P1 and P3 probably, but not P2.
But we would start here at T1 in the beginning of the path, and there's still an influence here of
No.
the second point. Yeah.
Then we probably wouldn't hit any.
Yeah, that's correct. Yeah, and so the path here would look roughly like this. And again, I drew here the influence of the basis function as gradients. So for example, if you here in the middle, then the influence of blue is the highest, and green and red are still contributing, but very little. And if you're here at the end, then you have a little bit of influence of blue and a lot of influence of green, and so you are closer to P1 than P2, and the same here for the end, where you have more influence of P3 and a little bit of influence of P2. Yeah, and the special thing about it is, of course, that you never hit here P1. If you actually still want to hit P1 and P3 because they are the start and end points of your path, then you can still do some tricks, but in the usual definition of it, you don't actually hit the control points. Okay, does that make sense? Any questions about it? Yes.
Right now I'm just a bit confused what the B functions actually are here in this case. Are they just the linear connections?
What do you mean with linear?
Basis functions like B1, B2, B3 that we get up.
Yeah, so the green one here is B1, blue is B2, red is B3.
Yeah, but like in the point space here.
Here?
Yeah.
So for each point here on the path, you basically are at one of the points here between T1 and T3. And so for example, if you're in the middle, then you're at T2, and then you would just compute basis function 1 times P1, basis function 2 times P2, and basis function 3 times P3. And in this case here, you would have, I don't know, 1 times P2 plus 0.5 times P3 and 0.5 times P1.
But what are the base functions?
So you mean the mathematical definition of those?
Okay, maybe this axis on the left represents how far we step on this B function, right?
No, so basically,
How much this B function is.
so the B function are just those graphs here, the green, blue, and red. So we have 3 basis functions, and then we have this interval of the path between T1 and T3. So you start at T1 and you end at T3, and the basis function are just telling you at each point here what is the influence of all the points.
But how do we get to x, y coordinates on the right hand? That's the main thing.
Oh yeah, so basically you have P1, P2, P3, they are defined by x and y. And so the basis function just tells you, for example, that you should compute 1 times P2, so you get x and y of P2, and then you get an influence also of P3 and P1. So you get basically, yeah, a linear weighting of the 3 control points.
Okay.
So basically x, y from P1 plus x, y from P2 plus x, y from P3, and then you weight them by the basis function.
Makes sense, yeah.
And then you get whatever on the right here.
I
Yeah. Okay, and something which here is a bit tricky is, of course, that sometimes you want to have a very specific differentiability of your splines, but it's usually a bit complicated. For example, if you want to have something which is C4 or C5, how do we actually do that? And there's a very nice method to do that, which is called the Cox-de Boer recurrence. It's basically a recursive basis function where you can choose an integer k, and depending on k, you get a certain level of smoothness. So for example, if you choose k equal 8, then you get a smooth function of C8. And in that way, you can basically tune dimensionality and smoothness. And I have written down here the recursive formula for it. So basically, you have as input here one basis function, which is 0 or 1 on your interval. And then based on that one, you recursively define all the other basis function up to k by this expression here. And so, for example, for the first 3, so if you have k equals 3, then you get those basis functions here. So one is the ones which are just square ones, and you have those triangles, and then in the end, for the third one, you have those Gaussian shapes, so those quadratic functions. And so basically in the end, your function would, in this case here, be at least C3, because you have chosen k equals 3. But of course, you can do that up to any dimension you want. So that is basically a very nice way to actually define it without going into some complicated things, and where you have to manually actually specify basis functions like that, which might be very complicated and you can't tune it. Instead, you can just take this very nice recursive function and you get whatever smoothness value you want. Okay, any questions about this before we continue? Okay, cool. Then the next topic will be polynomial splines. So polynomial splines are pretty important because they have actually very nice connections to convex optimization, and in the end we will see how we can actually directly optimize, for example, for low energy or smallest acceleration along a path. So yeah, a polynomial spline is basically defined here by the sum over some value ak times t to the power of k. So basically you have this sum here of different exponents, and so a cubic polynomial would be basically something where you go up to 3. And yeah, some small question here for you: what would be actually the values of this cubic polynomial at t0 and t1?
At t0 it would be just a0,
Yeah.
and at t1 it's just sum of all the a's.
That is correct. And what are the derivatives with respect to t at t0 and t1? So basically, sorry, now I just showed the answers. Yeah.
To 0 it would be a1, right?
Yeah. Would it be?
Like if we derive, like the first part a0 will fall, will disappear,
Mm-hmm.
and then every other part except like a1 will become constant, and like the other two will be 0 at that point, so it must be a1.
Yeah, that's right. Sorry to confuse you. already at t equals to 1. Yeah, exactly. So basically, the derivative here, the first one is a1 plus 2 a2t, and so on. And of course, if you just plug in here 0 and 1, you get a1 and the expression here on the right. Okay. Can you actually all see the expression? Yeah. Okay. All right. So let's assume that we have a trajectory and we represent it using polynomial splines. How do you think we can actually compute an acceleration cost? Anyone an idea? Okay.
Well, wouldn't it just be the second derivative of the position?
And something else?
Or the mass of the vehicle, but if you want to calculate the energy. But like the second derivative would just be the acceleration, and we could use that for the cost.
Well, yeah.
And I think we then also need to integrate this again, and because we only have like this polynomial, we can probably simplify the function quite a lot to get our acceleration or our integrated acceleration.
I guess maybe you have already thought about integrating it, but yeah. So basically, you were right that we can basically just take the second derivative, but then we also have to integrate it over the path, of course. And as you already said, it's of course pretty nice because we can simplify it a lot and we get to this very nice simple expression here, which is basically our cost to optimize for acceleration. So which basically minimizes acceleration over the path. Okay, let's look at an example where we have three numbers, x1, x2, x3 in R, and we want to connect them using two cubic polynomials. And we will use coefficients a and b. And so this can be actually casted as an optimization problem. Namely, we get the cost here of our acceleration for each of the polynomials. We just sum it up. And then we have some constraints, namely that in the beginning you want to be at x1. Then at the end of your first polynomial, you want to be at x2. In the beginning of your second polynomial, you want to be also at x2. And then in the end, you want to finish up at x3. And sometimes you also want to have, actually always you want to also have the derivatives matching up here between the polynomials at the point where they intersect. And this gives you the following expressions here. When you evaluate it, you basically get this here as a cost function, and you get those expressions here as constraints for your optimization problem. And in the beginning, we talked already about different types of optimization problems. Does anyone know in which category of optimization problem this one here falls into? Sorry again?
The gradient-based?
Well, that would be one way of how you could solve it. But what kind of type of optimization problem would that be?
I think it's a linear problem.
Yeah.
I wanted to say the same thing. Like, I don't see any quadratic components, so it should be linear.
Yeah, that's correct. So basically, the input here is a and b, so that would be our x. And there are no quadratic expressions here of a and b. And so this basically gives you already a hint that this is actually a linear program. For higher orders, this can actually become QP, quadratic program. But for the thing which we just saw here, it's LP. Okay, one more question: how can we handle the 2D or 3D case?
We
Mm-hmm.
So we have to do it like we split each coordinate into x, y, z, for example, and do it once for all the x part, one for all the y, and one for all the z parts.
Yeah, exactly. So you can basically do the optimization for each dimension independently. And yeah, there are still some challenges, even though this looks actually pretty good. So one challenge is numerical stability. So for example, if you have a very high order, for example, larger than 8, or a lot of different pieces because you have so many waypoints, then it's a bit difficult to solve in practice. Yes?
Yeah, I have a question, like why can we separate the dimensions? Because like in my mind, if we have maybe an acceleration of 2 in one dimension and 2 in like, you know, 4 in another one, but then like the actual acceleration would, can be computed like with the Pythagorean theorem, in my mind, and I don't see how we can just optimize them independently from each other, because like the resulting acceleration is what we actually want to optimize, right? And this is not a linear function of the individual components, right?
So why do you think this is not a linear function?
Like because like if I accelerate like 2 in the x direction and 2 in the y direction, the resulting acceleration would be like the square root of 2
2 squared plus
2 squared plus 2 squared,
Mm.
which would be like square root of 8, and like this is like a linear function of the individual dimensions, right?
So yeah, I think it might be that you come now to a point where you have to actually cast it as a QP. But yeah, actually I'm not sure about it, so I have to. I will check this for you.
Okay.
But yeah, I'm actually quite sure that you can make it independent. Right. Okay, yeah, back to challenges. So yeah, one, as I said, poor numerical stability. One solution would be, for example, to formulate it as an unconstrained QP, where decision variables are endpoint derivatives of the segments. This often gives you a bit more stability. And the second bigger problem is that, of course, with splines you cannot handle obstacles. So for example, if you have a path here, which is super close to obstacles, where you have, for example, one control point here directly at a corner and another control point again on a corner, and you just splinify it here, just putting a spline through, then very often you have a big deviation from your original path, and you might actually come here into an obstacle with your spline. And the way of how you can actually deal with that is by checking if the spline is actually collision-free, and if it's not collision-free, then you add additional waypoints. And you can see that here, the more waypoints we add, the more closer we actually come with our spline to the original path. Because we have added more segments, and we have more constraints on the segments, and so very often this actually constrains the path much more, and then we come to a point where you actually are feasible again. Okay, any questions about this? Yes.
Here, the splines always go through the initial waypoints, right?
Mm-hmm.
The way we define it. And for B splines, we could also do that, or could we?
Yeah,
Okay.
exactly.
So the main benefit of this is that it's differentiable.
Yeah, exactly. Of course, with B-splines you could also have differentiability depending on what kind of splines you use. But yeah, the nice thing about this one here is that you can directly optimize for minimal acceleration, minimal energy basically, and this is often something which you want in your system. Okay, let's look at one more type of splines, Bezier curves. They are actually important in robotics because we can actually use them to stay inside of safe regions in your configuration space. And so this is often pretty nice because you get this guarantee that you will not end up in an obstacle while still having a pretty smooth path. So Bezier curves are very similarly defined to our basis splines, but in this case here we have just a different basis function. So again we have here a Bezier curve of degree n. It's defined by n+1 control points, and the definition here is similar to the one which we already had here for basis splines, but instead here we have this expression for the Bezier curve where you have n over I times t to the power of I times 1 minus t to the power of n minus I. And so this expression here gives you the Bezier curves. And so one example of a Bezier curve would be this cubic Bezier curve, where you basically go all the way up until the third power. And here should be a small animation, which is not working right now. But basically, you could see here, if this would be working, that you follow the path and you have influences again here from P1, P0, P1, P2, P3, and this basically defines you the shape of the path. Okay, and Bezier curves have some certain properties which are pretty nice. One is endpoint interpolation. So whenever you have a set of control points, the Bezier curves will actually stay at the beginning and at the end on those control points. So this gives you basically guarantees that you will not go away from your endpoints, which was one of the problems for basis splines. And it gives you Cn smoothness. So whatever kind of n you have picked, this gives you also the corresponding smoothness class smoothness value. And apart from those two properties, which are pretty nice, we have also a third one, which is this convex hull property, which basically says that whatever kind of Bezier curve you get here, it will always lie inside of the convex hull of their control points. So basically, you have the set of n control points, and you compute the convex hull, and you can be 100% sure that whatever comes out here will always stay inside of this convex hull. And so here's a small visualization of this. So the lines here are separating hyperplanes. So basically, every line tells you that you have to stay on one side. And this gives you this region here, which here is the polytope. And we have a certain number of control points here. And the Bezier curve will always be in the convex hull of the control points, and also in this case here in this polytope, because the polytope contains all the control points. And so the question is, of course, why is this convex hull property useful, especially for motion planning?
Because it's guaranteed that if the control points itself, the convex hull of the control points don't collide with anything, the motion path will also not collide with anything.
Yeah, exactly. So whenever you have a region in your configuration space and you know that this region is free, and you know that all the control points are in there, then you can also be sure that your Bezier curve will be feasible. And yeah, so basically in the end your curve is guaranteed to be collision free, and this is a very nice property, of course, to have. And so this actually enables you to do motion planning with something which we call safe polyhedras. So the robot path here is in green. This could be just the path of like a point robot, and we have some obstacles in blue and red. And the way of how we can plan here with safe polyhedra is that for each of the edges here on your path, you compute a region, which is this one here, and this region is basically a safe polyhedra. It's basically a region in your configuration space which is guaranteed to be collision-free. And you do that here for every one of the edges, and this gives you this area here. And in the end, you can basically be sure that once you have this area and you have all your control points in those areas, then in the end you will get a smooth path of a defined smoothness value, which you can pick, and you are guaranteed to be inside of this area here. And this even works for the 3D case. So you might not see this here perfectly, but those are basically 3D polyhedras, which are safe regions in your configuration space, in your workspace, for example. And then in black you have like a zigzag path, which might be the output of a sampling-based planner. And then in magenta here you have a smooth Bezier curve, which is basically fitted over all the control points, and which is guaranteed to be actually inside of all the safe polyhedras here. And this is actually something which is very heavily used, for example, for planning with drones, or even planning with manipulator arms. Okay, any question about this one? Okay, so let me just wrap up splines. So the cool thing about splines is basically that we can optimize directly and very efficiently for smoothness and also, for example, for energy, for low acceleration. We talked a little bit about base splines and this recursive definition of them, which is pretty nice. I would say two of the most important splines are really polynomial splines, which you can directly use in combination with convex optimization to get very low energy paths. And then also Bezier curves are super important because you can do the safe planning where you have this guarantee that you will always stay feasible and not collide with any obstacles. Okay, and that wraps up everything about splines. And now I want to talk a little bit about gradient-based optimization on differentiable costs. So with splines you have of course some disadvantages because you are very restricted to optimizing a very certain cost function, namely one where you optimize, for example, the energy of the system or acceleration of the system. You also optimize for smoothness, but sometimes you have more complicated cost functions. You want to, for example, stay away from your environment. You want to be a bit more safe. You want to also be smooth, but taking all those cost functions into account is usually a bit more complicated, and in that case splines break down and you need to have some, I would say, more general framework of how you can optimize. And this brings us to this whole topic of optimization on differentiable costs. And the idea is basically that you take as input a path and you try to deform it into the direction of a lower cost. And the most fundamental concept here is the one of a functional gradient, which is basically the generalization of directions for paths. So basically, a functional gradient tells you in which direction you should deform a path such that it actually improves whatever cost function you have as input. And so cost functional, in this case here, could look like this. So for example, you have a path in your configuration space, and you might want to optimize something where you have different cost functions. For example, you have an obstacle cost, which tells you that you want to stay very far away from obstacles as possible. But at the same time, you might have a smoothness cost where you say, okay, I also want smooth paths. And then on top of that, you might have also a path length cost where you say, okay, I want to stay away from obstacles, I want to be smooth, but also I want to be having a very short path. And so if you have cost functions which are like that, which are much more complicated, then it often makes sense to compute gradients of all those cost functions and just do gradient descent in your functional space. And so basically, in the end, what you do is that you derive all those cost terms here, and you basically move the path into the direction of lower cost. So you basically move into the direction where your gradient points. So it's basically the same as for scalar functions. And this is the whole idea of optimization-based planning with differentiable cost functions. And so, how this would look like visually is basically that you get as input again like some kind of zigzag path, and then you have something which would be maybe like the optimal path here. And what you do is basically that you compute for each waypoint here a gradient, and this gradient basically points you in the direction of where lower cost would be for this path. So for example, those waypoints here, they are very close to an obstacle, so there might be like a gradient which moves this waypoint further down, and there might be also an influence of smoothness and also an influence of path length. And then you have multiple iterations of gradient descent, and this basically moves the path for each iteration closer to like an optimal path with respect to whatever cost function you defined as input. So this is the whole idea, and now we will look a little bit closer into how you can actually compute gradients of cost functions. And in particular, we will look at computing obstacle cost gradients, because this is basically one gradient which is very difficult to evaluate, and at the same time also super useful in practice, because it basically pushes you away from obstacles, and this is basically something which is almost always a good idea. Okay, so let me go a little bit into details here of obstacle costs. So the definition of an obstacle cost here in our case is basically that we define it as clearance from the environment. And so the obstacle cost would be basically an integral over the path and an integral over points on your robot. So B is our robot body. And then we would compute what is actually the clearance of this point here from my environment. So X is basically a pre-specified point on your robot body, and Cx is the minimum clearance to the environment, and S here in this case here is the index of the path. So let me show you a small example. So the cost at a specific configuration would be basically just the sum over all the clearances. And one way of how you would do that in practice is basically that for each link on your robot, you would compute what is actually the minimal distance to the environment. So for example, if you have like a complex manipulator arm here with a very specific welding gun here at the end, you can see here I draw some points here on the robot and some points here on the environment, and the yellow line here gives you the shortest distance between this robot body here and the environment. And you can do that here for multiple links on the robot body. You can also do that for links which are both on the robot body, and so this gives you basically an idea of how far are you away from obstacles or from self-clearances. And this basically gives you a certain measure of how costly the state here is. And so if you're interested, for example, in points or in configurations which are far away from obstacles, then of course it makes sense to go somewhere where all those clearances are actually maximized. So this is the general idea. And mathematically there are different ways of how you can define this clearance. So one way of how we can do that is basically by evaluating the distance of some point on your robot at a certain configuration. So we call it dx of q. And then this represents basically the distance from a point on your robot to the nearest point in the environment. And then we take, for example, a quadratic function of this, and this is basically tells you what is your clearance. Right, so that is basically how you define this, and then you just sum up over multiple points on your robot, and this gives you a certain cost, which is high if you are very close to an obstacle, and which is low if you are very far away from an obstacle. And so very often we choose functions like that, where you have like some kind of epsilon, so that, for example, points where you are above epsilon, they are not taken into account anymore, because that's basically a certain clearance which you are away from the environment, and then you don't care anymore about being close. Okay, and so the next step here is that we want to find an expression for the derivative of this cost function. And this requires two things which we need to do. One is that we have an efficient computation of distances. This will bring us to the signed distance field. And then we also need an efficient obstacle cost gradient. And so those two topics I will cover quickly. So let me start first with signed distance fields. So those are basically a way of how you can compute distances very efficiently, very cheaply. And the signed distance field is actually required because we have this big problem here. So if you want to actually compute distances of a point to the environment, then this is usually not very trivial, because for each point you need to compute the clearance, and in the worst case, I think we had this already in lecture 2, that you had this GJK algorithm which you run to find actually the nearest point between two convex bodies. And so, for example, if you're in an environment where you have hundreds of obstacles and maybe tens of robots, then you have to check for each of the convex bodies here, how close are they actually. And if you just iterate over all of them and you use that for every configuration, then this can become very, very expensive quickly. And so that is why we need a better way of how we can compute distances. And so signed distance fields are a very nice way of how we can actually approach this. We assume here that all obstacles are static. Of course, the robots can just move around as they wish, but we assume that all obstacles are static. And if they are, then we can just pre-compute something which is called a signed distance field, and this signed distance field basically assigns for each point in space its clearance value to the environment. So let me give you just a visualization of that. So what you see here is a 2D plane and a grid over this plane. And for each point, we have computed how far is it actually away from an obstacle. So for example, something which is red is very close to an obstacle, green is like intermediate distance, and blue is away from obstacles. And so this distance field can actually be computed pretty efficiently, and once you have computed it, you can use it over and over again in your cost function. And this can also not only be computed efficiently in 2D, but also in 3D. And the idea is that you voxelize your environment with a certain coarseness, and then for each voxel you compute the nearest obstacle distance, and then you store this information and you use it as a lookup table basically to compute clearances. One of the most famous algorithms to do that is actually the marching parabola algorithm. Let me just see, I think we still have time to cover this. So the marching parabola algorithm is basically one way of how we can efficiently compute signed distance fields. So the idea is that we have V, which is our grid, and P are all the occupied voxels on the grid. And then you want to search for a function which we call dp of V, which is the minimum over all the occupied voxels and the distances to these occupied voxels. And the idea for this marching parabola algorithm is basically that you compute the lower envelope parabolas for all occupied voxels, and then for each point you check the height of this lower envelope and store this value. And so this idea is basically that you have here, for example, in 1D, you have different points here. For example, VK, it's an occupied voxel, so you have many different occupied voxels here. And for each one, you draw a parabola, and then you compute what is actually the lower envelope of all those parabolas. And so the black line here would be the lower envelope. And you try to compute this because this would be actually a very efficient way to later on compute the signed distance field. And so, yeah, what you need to do here is first establish the number k, which is the number of parabolas in the lower envelope. So k is basically just the number of occupied voxels. And then you have p of I, which is the location of each parabola in the lower envelope. And then you have z, which is the range of each of the parabola in the lower envelope. So basically, what you do is that you try to come up here with certain subsets on which all these parabolas are defined so that you can have actually a representation of this lower envelope. The algorithm for that one is shown here. I will just quickly go over it. So basically the idea is that you start on the left, you compute one of the parabolas, then you move on to the next occupied voxel, you compute again a parabola, you try to find out what is the intersection point of them, and this basically gives you two lower envelope parabolas, and then you can just chain them together. And so that is why it's also called the marching parabola, because we go from the left and we add one parabola at a time, and we recompute the lower envelope. Okay, and then once you have it, you just basically go over all your voxels, and for each point you compute what is actually the value in my lower envelope, and this gives you, in the end, the signed distance field. Okay, and something very nice about this is actually that we can reduce the multidimensional case to the one-dimensional case. So for example, if you have a 2D grid, then the expression for the signed distance field of two variables, x and y, it can actually be simplified to an expression where you compute first the signed distance field for y, and then you use it as an additional input scalar for the problem of computing the signed distance field for x. And this is pretty nice because now you have a computational complexity of O of dn, where d is the dimension and n is the number of points. And yeah, if you want to look a bit closer at this one, there's also this publication here, Distance Transforms of Sampled Functions, which explains this all into detail of how you can actually convert this to this one-dimensional case. Okay, so again, why did we actually do that? Because we wanted to have the signed distance field which tells us for each point in space how far is it actually away from obstacles. And so this can be directly plugged in into our clearance and gives us a very efficient way of how we can compute the clearance cost. So now that we have that one, the next step is to actually compute directly the gradient of the obstacle cost. So that is our next step. So to compute the gradient, we need basically three steps. The first one is that we need to compute the gradient of the clearance, which we just defined. Then we consider the gradient as virtual forces. And then in the last step, we will map forces into the configuration space. So let me just quickly go back to our initial example here. So basically, if our cost is defined by the clearances here, then one way of how you can actually improve the cost is by looking at each of the clearances as some kind of virtual force which is acting on the robot. So for example, if you want to increase the clearance, then of course it makes sense to push the robot away so that the clearance locally at each of the points here is increased. And so basically each of those yellow lines here could be thought of as a virtual force which is acting on the robot. And what we need to do is sum up all the forces, project them into the configuration space, and then find a direction in the configuration space into which we move the robot such that it is actually locally maximizing all the clearances here. So that is the basic idea. And the way of how we can compute this is that first we compute the gradient of the clearance. So yeah, as I said, the clearance will basically be improved by moving point X away from obstacles. The point X, as you remember, was the point of the robot. So let's say that we have NE be the nearest point on the environment to X. Then we can just compute a direction, as just the norm, so just the normal between X and NE, which is basically just the direction into which we would push the robot so that we can improve. The second step is that we consider those directions now as virtual forces, where we push at each X into the direction of the gradient, and this would increase clearance. And so now we have to define virtual forces at each X and map them into the configuration space, which is basically the third step. So basically the idea is that each virtual force will move a point by a very small dx. And this in turn, if you push the robot with a very infinitesimal small dx, then of course the robot will answer by moving a little bit with dk in the configuration space. So the actuators will move, and dq in this case will be basically a direction in configuration space which locally increases our clearance. Okay, so how do we actually do that? It's very simple. You just take the derivative of the forward kinematics. So if you had already like a robotics course, then you might remember those formulas here. So let's say that we have x, which is a point in the workspace on the robot, and q is our current joint space values, and t is our forward kinematics. So the forward kinematics basically map configurations to a point in the workspace. So this is basically the first equation here. And we can very easily also take the derivative of this. So basically the velocity here, or the displacement of x, is equal to the derivative here of the forward kinematics times the derivative of the joint space values. And this expression here is a Jacobian. It's basically the first derivative of the matrix. And what this expression here does is basically it relates small displacements in the configuration space to small displacements in the workspace. And if you now take the inverse, you basically get a representation of small displacements in workspace to small displacements in configuration space. And the way of how you do that is by taking the inverse of the Jacobian, and in practice very often people also use the transpose or pseudo-inverse because it's a bit more numerically stable. But yeah, this is not super important right now for getting to the gradient. Okay, and then you just plug this into our equation and you get a functional gradient which tells you into which direction you should actually move your whole path. And this can be used then again, as in the beginning, as a descent step in functional space. Okay, just quickly let me recap this. So the idea was basically that we formulate the cost from distances, we compute virtual displacements in the direction of the decreasing cost, then we map those virtual displacements into the configuration space using our Jacobian, and then we take those displacements as directions for a gradient step in functional space, and then we just apply gradient descent to it, and we get a path which is farther away from obstacles as before. And one of the most important algorithms which actually use this concept is CHOMP. So CHOMP stands for Covariant Hamiltonian Optimization for Motion Planning. It's basically just a framework which encapsulates all what I just talked about. the idea here is basically that you initialize a path, you discretize a path, you use this cost function which I just mentioned, and you apply derivatives to each of the waypoints, and you repeat this until some termination criterion, for example, the magnitude of the gradient falls below a threshold. And here are some examples. So what you can see here is a 2D optimization of the path with the signed distance field laid on top. And you can see here, after multiple iterations, this algorithm is actually converging to a pretty good path, which is far away from obstacles while also being smooth at the same time. So in 2D it works, in 3D it also works. So for example, here's the manipulator arm, where we start actually with a path which is in collision, and Chomp is actually able to move this out of collision and also arrive at a very smooth path, which is also optimizing the clearance from the environment. Okay, and one question for you. What do you think about completeness and optimality of this approach? Do you think this is complete? Anyone an idea? Yes.
I think in general it's neither, right? Because it will only find the local optimum, and so by this definition we definitely can rule out optimality if there's some global optimum that we'll never find, and like if we are unlucky and our local optimum is also not a valid path, but there exists a global optimum which is valid, then that wouldn't be complete.
Yeah, that's correct. So if you start with a feasible path, then of course this retains completeness, and for optimality you only converge to something which is not necessarily global. Yes.
If I start with a like epsilon suboptimal path, like a path which I know is not optimal but globally near optimal, this should converge to the globally optimal path, right? If like I am if my gradient is also within this like epsilon.
So I think you can definitely make some statement about this. In general, I'm not completely sure. For example, if you have still like an obstacle in between, which is very tiny, and you can't detect it correctly, then I guess even if you are very close to the global optimal solution, you might still fail. Any more questions? Oh, yeah.
Is there a reason that we have to pre-compute always the signed distance field, or would it also be possible to like calculate the voxels on demand?
Yeah, I mean, of course, you could also just compute it on demand, but it's just a very efficient way to compute clearances. And I think it's very difficult to compute clearances without a signed distance field. It's very costly.
But you have to have the full field, not really, but you could also like,
The what?
you have to have the full field, or would
Oh,
it
you
be
mean?
enough to just like if you need a certain voxel just to compute it on demand when you need it?
So like a cache, basically.
Yeah.
Yeah, definitely possible. Okay, let me just summarize. So we talked about optimization-based motion planning today, and especially about two different categories, gradient-free and gradient-based. In gradient-based, we had derivatives of cost functions to optimize our path. We talked a little bit about shortcutting as an example of gradient-free optimization. And then I went a little bit deeper into splines, B-splines, polynomial splines, especially for optimizing energy or acceleration. I talked about Bezier curves to optimize smoothness, even so with obstacles, so that we can basically be sure that we stay in a safe region. And then I talked about gradient-based planning with differentiable costs, and I went a little bit deeper here into obstacle costs because they are so important, and we talked about sign distance fields and obstacle gradients. And finally everything came together in this gradient descent and Chom, which is basically a framework which can optimize over general cost functions as long as those cost functions are actually differentiable. And that's basically everything for today. Yeah, thank you.